Introduction to Dynamical Systems, Part 6, Bifurcations of Fixed Points. Generally, dynamical systems can depend on some control parameters. In the previous part, we considered van der Pol equations, which depended on parameters epsilon and omega naught. We observed that the stability of the fixed point in the van der Pol equations depended on the values the control parameters were taking. Namely, at a certain combination of control parameters, the fixed point was stable. When the parameter values changed, the stability of the fixed point changes too. Generally, when the parameters of a dynamical system change, the fixed point can change its stability, or it could appear, or it could disappear altogether, or it can give rise to a new object in its vicinity. For example, nearby the fixed point, a limit cycle could be born. These changes associated with the fixed point are related to the concept of a bifurcation in a dynamical system. It is obvious that when the fixed point becomes stable, or when it disappears altogether, or perhaps when a completely new object is born in the phase space, the behavior of the system changes drastically. We can introduce the concept of a bifurcation as a qualitative change in the behavior of the dynamical system when the parameters change. For the fixed points, there can be several bifurcations, some of which will be considered in this lecture. We will start from considering a saddle node bifurcation, and we will consider the saddle node bifurcation in the one-dimensional system for the start. Consider the simplest, the minimal model in which saddle node bifurcation can occur. It is described as follows: x dot is equal to a parameter r plus x squared, which defines the function f of x in the right-hand side. Because it is a one-dimensional system, we can draw the phase line diagram for it by plotting the function f against x. The function f is represented by a parabola which, for negative values of r, intersects 0 at 2 points. These 2 points are fixed points of this system. We can find these fixed points by setting f of x to 0, and these fixed points appear to be equal plus minus of the square root of minus r. Since r is negative, minus r is positive, so the square root is real. If you remember, the eigenvalue for this fixed point will be the value of the derivative of the function f taken at the fixed point. So consider the fixed point which corresponds to a negative value of x, minus square root of minus r. Its eigenvalue lambda is equal to the derivative of f, which is 2x, and if instead of x we substitute minus square root of minus r, we obtain minus 2 square root of minus r, which is a negative number. So a negative eigenvalue means that the fixed point to the left is stable. Consider the case when r is equal to 0. The parabola depicting f of x now touches 0 axis, and there is only one fixed point. This fixed point is located at 0. The derivative of f at this fixed point is equal to 0 too. What does that mean? The eigenvalue is neither negative nor positive. It is 0. The fixed point is neither totally stable nor totally unstable. When we set the initial conditions to the left of the fixed point, the phase trajectory converges to the fixed point, but when the initial conditions are set to the right of the fixed point, the phase trajectory goes away from the fixed point. This is what is called a bifurcation point. The system changes its behavior quite a lot. Now, when r takes positive values, the parabola does not intersect zero value and there are no fixed points at all. If we set initial conditions in the negative part of the graph, the phase trajectory simply goes towards positive values of x and does not stop. So as compared to the negative values of r, at positive values of r, the system changed its behavior drastically. This bifurcation is called saddle node bifurcation. Why saddle node? Let's see. It's because at negative r, the system had two fixed points. The one at the left was stable, but the one at the right was unstable or saddle. A saddle would apply to high dimensional systems. As r grew, the two fixed points were getting closer to each other, and at the bifurcation value of r at 0, they met, they collided. And after the bifurcation point, they disappeared altogether. Both of them disappeared. So this is the saddle node bifurcation in a one-dimensional system. Saddle node bifurcation can also occur in systems of high dimension. Consider how it happens in a two-dimensional system. Consider the phase plane, and suppose our system has a control parameter called alpha, and suppose that the bifurcation value of this parameter is alpha with subscript Sn for saddle node. When alpha is smaller than its bifurcation value, in the phase plane there are two fixed points. One is a stable node at the left, and the other is a saddle at the right. When the parameter alpha grows and approaches its bifurcation value, the two fixed points come closer together. And when alpha reaches its bifurcation value, they collide and disappear. When alpha exceeds its bifurcation value, there are no fixed points in the phase plane any longer. What happened as a result of this bifurcation is a drastic change in the system behavior. Namely, before the bifurcation, starting from some initial conditions, the dynamical system converges to the fixed point, which is stable. But after the bifurcation, from the same initial conditions, the dynamical system will either go to infinity, or if there are some other attractors in the phase plane, it would converge to these attractors. There can be a special case of a saddle node bifurcation that occurs on a closed curve. Namely, it is possible when two fixed points sit on a certain closed curve, as is shown here, with a stable fixed point shown to the left and the saddle point shown to the right. Before the bifurcation, the 2 points are separated by a certain distance, but as the parameter value approaches its bifurcation value, they come closer together. When the parameter value takes its bifurcation value, the 2 points collide and disappear, and after the bifurcation, there are no fixed points any longer on this closed curve, and the closed curve becomes a limit cycle, which is an attractor. So what happens to the behavior of the dynamical system as a result of this bifurcation? Before the bifurcation, starting from some initial conditions, the system converged to the stable fixed point, and it would not even know about the existence of the closed curve or about another fixed point. However, after the bifurcation, the system converges to the limit cycle, which means that it starts oscillating periodically with a certain frequency. This example of a saddle node bifurcation is a remarkable illustration of how periodic oscillations can be born in a dynamical system. The second bifurcation occurring to a fixed point is called Andronov-Hopf bifurcation. For this bifurcation to occur, the dynamical system needs to be of dimension 2 or of a higher dimension. This bifurcation can take place provided that the fixed point has two complex conjugate eigenvalues, and at the bifurcation, their real parts are equal to 0. Andronov-Hopf bifurcation is named after two mathematicians, Andronov and Hopf. As a result of this bifurcation, the dynamical system can develop self-oscillations, periodic self-oscillations. Andronov-Hopf bifurcation comes in two versions. The first version is supercritical. Consider the phase plane before the bifurcation. Before the bifurcation, we assume that the fixed point was a stable focus, which meant that the real part of its eigenvalues was negative. Suppose the control parameter of this system is changing and approaching its bifurcation value. At the instant of bifurcation, the real part of the eigenvalues of the fixed point become 0, and the fixed point becomes a center. When the control parameter exceeds its bifurcation value, the real part of the eigenvalues is now positive, so the fixed point becomes an unstable focus, which means it is not an attractor any longer, but around the fixed point a new object suddenly appears, called a limit cycle. A limit cycle is an attractor, and it is an oscillating attractor. So as a result of the supercritical Andronov-Hopf bifurcation, the dynamical system changes its behavior from converging to a stationary point to developing sustained periodic oscillations. The second version of Andronov-Hopf bifurcation is called supercritical bifurcation. Before the bifurcation, the phase plane should contain a stable fixed point, which should be a stable focus, just like with the supercritical case. However, in addition to that, in the phase plane there should exist an unstable periodic orbit, which is not a limit cycle. Interestingly, if we set initial conditions inside the unstable periodic orbit, the phase trajectory converges to the fixed point. But if we set the initial conditions from outside the periodic orbit, the phase trajectory goes to the infinity. So the periodic orbit serves as a separator in the phase plane. It separates two different kinds of behaviors. Now suppose the control parameter of this system is changing in such a way that it gradually approaches its bifurcation value. As it happens, the unstable periodic orbit shrinks and approaches the fixed point, so that at the moment of bifurcation it collides with the fixed point. At this point, the real part of the complex conjugate eigenvalues of the fixed point take 0 values, and the fixed point becomes a center, just like in the previous supercritical case. However, after the bifurcation, although the fixed point changes its stability and becomes an unstable focus, just like in the previous case, no limit cycle is born, which means that there are no sustained periodic oscillations in the system. So two versions of the same bifurcation unfortunately cannot be distinguished between based on the analysis of eigenvalues alone. If you want to find out which version of the bifurcation occurred in the given case, we need to look beyond the eigenvalues. So we need to explore the phase space around the fixed point. Let us consider an example of a system in which Andronov-Hopf bifurcation occurs. Our example is going to be van der Pol oscillator, whose fixed point is at 0 and whose eigenvalues are given in the box. Let us consider the case when the expression under the square root is negative. In that case, the eigenvalues are complex conjugate. The fixed point appears to be a focus, and the phase trajectory spirals around the fixed point. We already know that epsilon is a control parameter of this system, and when epsilon is 0, the real part of the eigenvalues is 0 too, and the focus is stable. Now, when epsilon takes positive values, the focus is unstable. We conclude that something happens when the parameter epsilon takes 0 value. This is bifurcation, and this is Andronov-Hopf bifurcation. I can tell you that in van der Pol equation, Andronov-Hopf bifurcation comes in the first version, so it is a supercritical bifurcation, as a result of which a limit cycle is born, giving rise to periodic self-oscillations in this system. We learned already that the stability analysis of the fixed points can give us some qualitative information about the behavior of the dynamical system. It can tell us whether the dynamical system converges to a certain fixed point or perhaps goes away from the fixed point, but it does not tell us where exactly. So the linear stability analysis tells us something about the behavior of the system, but at the first glance, not too much. However, I would like to show that the linear stability analysis can also give us some quantitative estimates of the behavior of the system. Consider Andronov-Hopf bifurcation, as a result of which the limit cycle is born. And initially, the limit cycle is very small. At the bifurcation point, it has size 0. But when the control parameter exceeds its bifurcation value, the limit cycle grows, so its amplitude grows. How exactly is this amplitude growing? When the control parameter is changing. Remarkably, there is a mathematical result which can help us to estimate the amplitude of the limit cycle at some values of control parameters reasonably close to their bifurcation values. Namely, if our control parameter is called mu and its bifurcation value is called mu AH for Andronov-Hopf, the amplitude of the limit cycle can be approximately calculated as the square root of the distance between the current value of control parameter and its bifurcation value. This law is illustrated by the figure in the left-hand side of this picture, and it shows the amplitude of the limit cycle as a function of mu. And of course, the amplitude of the limit cycle grows when we go away from the bifurcation point. The figure in the right-hand part of this picture illustrates various limit cycles in van der Pol oscillator calculated at different values of mu, and mu here is the same as epsilon in our previous analysis. So epsilon, called mu here, is a control parameter. When mu is small, the limit cycle is small and it is a relatively smooth curve. When mu grows, the limit cycle grows too, and it is slightly distorted when we go away from the bifurcation point. So that is already quite a remarkable mathematical result. But is that everything we can learn from the linear stability analysis? Not quite. There is something else we can learn. In particular, we are probably interested to know the period of the newly born periodic oscillations. And remarkably, this period is provided by the values of the imaginary part of the eigenvalues of the fixed point. The period can be found using this formula. So, although the linear stability analysis of the fixed points does not promise too much, at least at the first glance, in reality, we can learn surprisingly many things from this analysis. We considered fixed points and their stability, but it would be interesting to discuss some more complex attractors. Unfortunately, it appears to be virtually impossible to find more complex attractors, such as periodic orbits, tori, and chaoses, analytically. And we have to reduce to numerical techniques. The problem with such attractors is that their phase plotted around these attractors might be quite confusing. And for example, a few illustrations of these objects are shown in this figure. In the figure to the left, we see a sample limit cycle revealed by numerical simulation in a special dynamical system called Oregonator. In the middle picture, we can see a sample torus, invariant torus, which lives in a three-dimensional space, and the torus is two-dimensional itself. And the figure to the right shows some sample chaotic attractor. The problem is that particularly with chaotic attractors, it might be very difficult to see the inner structure of this geometric set, and even if we depict the phase trajectories on the attractor in the three-dimensional space, we might not really see much. And it might be a little bit premature to say this at this stage, but I can tell you that even for the torus we can have some complications, because on the surface of the torus there can be some limit cycles which coexist. So it would be good to come up with some technique which would allow us to clarify the picture, at least visually. It appears that such a technique exists, and it is due to the famous mathematician of the 19th century, Henri Poincare. This approach is called Poincare section. What does it do? Consider a three-dimensional space for the start, and in the three-dimensional space there are some phase trajectories, infinitely many phase trajectories. So in this space we can introduce a surface such that all trajectories intersect with this surface at a non-zero angle, which means the trajectory is not allowed to touch this surface. So if we can find such a surface, this surface has a name, Poincare secant surface. Now we collect all points of intersection between the trajectory and the surface, but only in one direction. For example, as we can see in this picture, we record only points of intersection from left to right. And the full collection of such intersection points is called Poincare section. Suppose we have a periodic orbit which is a one-dimensional curve in the three-dimensional space, and its Poincare section will be just one point. If the periodic orbit is stable, the point of intersection will be a stable fixed point. If the periodic orbit is unstable, its intersection will be an unstable fixed point, and if the periodic orbit is saddle, its intersection is a saddle fixed point. Now for the two-dimensional torus, the Poincare section is going to be a closed curve. We can see that introduction of the Poincare section allows to simplify the situation and to decrease the dimension of the problem by 1. Basically, the limit cycle becomes a point, the invariant torus becomes a one-dimensional curve. Poincare sections are generally helpful, particularly in the context of synchronization, which we will consider further. And I would like to acknowledge help from Olga Sosnovtseva, Anastasia Niganova, and Dmitry Pasnov.